Welcome back to my class in problem solving, mathematical investigation, and modeling. Today we will introduce a new topic called mathematical modeling. What is mathematical modeling? Mathematical modeling is the process of developing a mathematical model. Mathematical modeling is a process in which real-life situations are expressed by using mathematics. Mathematical modeling is a cyclical process in which real-life problems are translated into mathematical language, solved within a symbolic system, and the solutions tested back within the real-life system. What are models? Models are abstractions of reality. Models are a representation of a particular thing, idea, or condition. Models are simplified representations of some real-world entity. Because mathematical modeling is said to be a process, it consists of several stages or steps. And we will discuss the 4 stages in mathematical modeling in the next lesson. And the outcome of a mathematical modeling, the process of mathematical modeling is called a model or mathematical model. A model is a representation of a system or a thing, a process. In particular, a mathematical model usually consists of a set of equations that are said to be true or to hold true under the given conditions or under the assumptions made. With these assumptions, the equations will only hold true for that particular model that represents a system in reality. Particularly, a mathematical model is a description of a system using mathematical concepts and language. And the language of mathematics uses symbols, signs, and equations. A mathematical model is a representation in mathematical terms of the behavior of real devices and objects. A mathematical model is a representation of the essential aspects of an existing system or a system to be constructed, which presents knowledge of that system in usable form. Now, why do we need models? Andrea Doshel Wilson gives 2 reasons why we need models. Number 1, models provide a framework for conceptualizing ideas about the behavior of a particular system. Number 2, models allowed us to find structure in complex systems and to investigate how different factors interact. Another reason why we need models, models play important role in informing policies. Informing policies means that models are used as basis for policy decision making or for evaluating the effectiveness of some policies implemented. And this is achieved by the following: by providing understanding of underlying causes of a complex phenomenon. This means that by studying the model, which is a representation of an actual system in reality, we can learn to understand why a system works or why the system is not working as it should. And number two, by predicting the future. Many models are used as a tool for forecasting. That is for making prediction for the behavior of the system in the future. And number three, models can be used for predicting the impact of interventions. And the impact is said to be significant if it creates a significant change or improvement in the performance of a system. Why do mathematical modeling, or why do we have to undertake this activity, mathematical modeling? And these are some of the reasons. Number one, for scientific understanding. A model embodies a hypothesis about the system, and the model lets us compare that hypothesis with data. A model is also often most useful when it fails to fit the data, because that would tell us that some of our ideas about the study system are incorrect, and that's the time that revisions are to be made. Mathematical models as well as computer simulations are useful experimental tools for building and testing theories, for assessing quantitative conjectures, for answering specific questions, for determining sensitivities to changes in parameter values, and estimating key parameters from data. Another reason why we do mathematical modeling is that many things or many questions are clarified by studying a model. The model formulation process clarifies assumptions, variables, and parameters. The process of formulating an ecological model, for instance, is extremely helpful for organizing one's thinking, for bringing hidden assumptions to light, and identifying data that are needed. Related to the first reason why we do mathematical modeling for scientific understanding is because once we have scientific understanding, we can better manage the world. Forecasting diseases or pest outbreaks can prepare the government agencies to manage the spread of the disease or to control the pest outbreaks. Designing man-made systems, for example, biological pest control and bioengineering, are some of the ways by which man can better manage the world as a result of having scientific understanding and managing existing systems such as agriculture or fisheries, where models are often used, and models are used for optimizing medical treatments. Many mathematical models are often used in simulated experimentation, and that is another one reason why we do mathematical modeling for simulated experimentation, because many In many cases, realistic experiments may not be possible, like experiments with infectious disease spread in human population are often impossible, unethical, or expensive. Also, we cannot manage endangered species by trial and error. So we would construct a model, like a survival model for the endangered species. And we also dare not set dosage for clinical trials of new drugs on humans or set safe limits for exposure to toxic substances without proper knowledge of the consequences. That is, there is a risk of using humans for clinical trials or experimentations. So, what is being done is to construct instead a model that would simulate the effects or consequences of these different dosages of the medicine that is being tested. And another reason why we do mathematical modeling is it is practical to do mathematical modeling. Sometimes a purely experimental approach is not possible because the data requirements for estimating a model grow rapidly in the number of variables. So instead of using a real actual experiment, we do a model of the system that we want to study. And modeling using computer programs is much cheaper and practical. Principles of mathematical modeling. These are standards that should be followed and are followed by many individuals who do mathematical modeling and undergo the process of creating a model of some system. The principles of mathematical modeling are meta principles phrased as questions about the intentions and purposes of mathematical modeling. This means that the principles of mathematical modeling are expressed as questions for which the person who is doing mathematical modeling has to answer sufficiently and honestly. Mathematical modeling is a principled activity that has both principles behind it and methods that can be successfully applied. And as I said, the principles are meta principles phrased as questions about the intentions and purposes of mathematical modeling. These meta principles are almost philosophical in nature. This is the visual representation of the basic philosophical approach. These methodological modeling principles are also captured in the following list of questions and answers. The first question is why? What are we looking for? This is the first principle of mathematical modeling expressed as a question using why. And to answer this question, you must answer the question, what are we looking for? And to answer this question, you must identify the need for the model. Why do you have to have a model? And the next is find. To answer this question, You must answer what do you want to know. And in order to answer that question, what do we want to know or what do you want to know, you must list the data you are seeking. And the next question is about the given. The question to be answered is, what do we know? What do you know about the model, the variables, or parameters? And to answer this question about the question on what do we know, you must identify the available relevant data. And the next question is about the assumption of the model. What can we assume? To answer this question, you must identify the circumstances that apply. That is the conditions that apply only for that particular model that you are constructing. When we are very sure about the purpose of our constructing a mathematical model, and we know what data are given and what data we are seeking, and we also made the assumptions that hold true only for the model that we are constructing. The next question to answer is the question of how. How should we look at this model? And to answer that question of how, you must identify the governing physical principles. And as we said earlier, most models are used for prediction or forecasting. So the next question to ask is the question on what will our model predict? And to answer that question, you should identify the equations that will be used, the calculations that will be made, and the answers that will be obtained from the equations and the calculations. Once you obtain the results or the answers and you have made predictions, the next question to ask is about the validity of the predictions and the results. Are the predictions valid? To answer this question, you should identify tests that can be made to validate the model. That is it consistent with its principles and assumptions? And the next question is the question on verifying the results or predictions made. The question to be answered is, are the predictions good? To answer this question, you should identify tests that can be made to verify the model. That is it useful in terms of the initial reason it was done? After the results and predictions have been verified using the appropriate tests, you now ask the questions of how the model can be improved. Can we improve the model? To answer this question, you should identify parameter values that are not adequately known, as well as variables that should have been included and or assumptions or restrictions that could be lifted. You should implement the iterative loop that we call model, validate, verify, improve, predict. Again, this is the cycle for mathematical modeling, which was defined earlier as a cyclical process, and the cycle starts from model, validate, verify, improve, predict. And the last question to be asked is on the usefulness of the results. How will we exercise the model? What will we do with the model? That is how the model can be used in the real world. Again, from the diagram, the process of modeling starts with an object or a system for which you want to create a model, that an object or system that you want to study. And you must be very clear about the purpose of your model, the reason why you want to construct a model. And you should also be very clear about the data you are seeking or what information you want to derive from the model. And once you are very clear with the question of why and find what do we want to know, that's the time you will now start constructing the model by first identifying the variables and parameters, identifying the given information, what is already given, and by making certain assumptions. And then you consider how you would look at the model using some physical principles. And once the model is constructed, you use it to derive a result or solution or prediction. A prediction that has to be validated and verified using tests. And once the predictions or results have been verified, you answer the question of how to improve the model. This list of questions shown in the diagram is not an algorithm for building a good mathematical model. However, the underlying ideas are key to mathematical modeling, as they are key to problem formulation generally. Hence, we should expect the individual questions to recur often during the mathematical process, during the modeling process, and we should regard this list as a fairly general approach to ways of thinking about mathematical modeling, which means that this list of questions shown in the diagram should guide you on how to think about constructing a mathematical model. A mathematical model is far from perfect because there are limitations of mathematical models. The first limitation is the lack of quantifiable knowledge. Models that encompass mechanisms, for example, infection process, require quantitative understanding of these mechanisms in order to make reliable predictions. And for this particular example, infection process, it is seldom that we have a quantifiable knowledge, a knowledge about infection process that can be quantified. Because in many of the mathematical models, we work with quantities. And in many instances, there are many systems whose variables cannot be quantified or expressed as numbers. The second limitation of mathematical models is the lack of available data or methods for estimating model parameters. For example, how do we estimate individual susceptibility and infectibility? Much improvement to be expected over the next years due to recent advances in statistical inference and data explosion may help us to solve this limitation or address this limitation of mathematical models, the lack of available data. And the third limitation of mathematical models is the inherent stochasticity of the biological system. Like infection is a stochastic process, and in many cases it is impossible to make accurate predictions for infection spread on the individual level. These are the different types of mathematical models, and this is how mathematical models are classified. Mathematical models are classified as either deterministic models or stochastic models. Deterministic models have no components that are inherently uncertain, meaning deterministic models have no parameters that are characterized by probability distribution, like the models that we find in linear programming. While in stochastic models, many of the parameters or almost all of the parameters are characterized by probability distribution. That is, stochastic model is characterized by uncertainty. Mathematical models can also be classified as static models or dynamic models. Static models are at an equilibrium or steady state as opposed to dynamic models which change with respect to time. Thus, static models are characterized by constancy or a condition known as steady state, where every variable remains constant. While in dynamic model, time is an element, like in many of the forecasting models. Mathematical models can also be classified as continuous models or discrete models, like models that contain differentials and models that contains difference equations. Model that contains differential equations may be classified as continuous model. A model that contains difference equations is classified as discrete model. Mathematical models can also be classified as individual models or structured models. Structured models are based on age, size, stage, and others. Mathematical models can also be classified as mechanistic models or statistical models. Statistical or empirical models are usually regression based. They provide a quantitative summary of the observed relationships among a set of measured variables. On the other hand, a mechanistic or scientific model begins with a description of how nature might work and proceeds from this description to a set of predictions relating the independent and dependent variables. And lastly, mathematical models can be classified as qualitative models or quantitative models. Qualitative models lead to a detailed numerical prediction about responses. Again, quantitative models lead to a detailed numerical prediction about responses, while qualitative models lead to general descriptions about the responses. Again, the deterministic models assume that the outcome is precisely determined by the model inputs and relationships. Deterministic models ignore all random variation. And in deterministic model, a given input produces the same output. In stochastic models incorporate inherent randomness. These models are characterized by uncertainty, and they use a range of values for the model variables in form of probability distributions, as I already mentioned earlier. And the same input produces an ensemble of outputs. The empirical models, also called as statistical models, are data-driven modeling approach. And it's their starting point are data obtained from empirical studies. That means actual experiments and observation. And the aim of most statistical models is to determine patterns and relationships between data or model variables. The empirical models or statistical models require no prior knowledge. And mechanistic models, also known as process-based models. Again, mechanistic models are also known as process-based models. These models are hypothesis-driven modeling approach. Their starting point is a specific phenomenon of interest that is observed from data. And the aim of most mechanistic models is to provide understanding for underlying mechanisms of the phenomenon that has been observed. Mechanistic models require prior understanding of a system, unlike the statistical model that requires no prior knowledge of the underlying system. In mechanistic models, data are used to validate the model. Finally, there is also what is known as simulation model. What is a simulation model? Simulation models are not specific types of mathematical models. The term simulation model refers to the process of implementing mathematical model, like through computer simulations. Simulation models usually simulate the process of data generation, assuming the model was true. For example, simulation of an epidemic or the within host infection process, and simulation of an experiment. And that concludes our lesson for today on the background on mathematical modeling. In the next lesson, we will discuss or take up the four stages of mathematical modeling. Thank you for joining me in my class today in problem solving, mathematical investigation, and modeling.